At the heart of the Milky Way hides a monster, a supermassive black hole called Sagittarius A. It bends light, swallows matter, and shapes the galaxy itself. But how does something so invisible control so much? Together we'll uncover its secrets. If this fascinates you, please like, subscribe and share, and tell us in the comments, if you could ask a black hole one question, what would it be? Thank you for watching. Now let's begin. The story of Sagittarius A star begins with the effort to look into the very center of the Milky Way. For most of human history, the central region is hidden from view by thick lanes of interstellar dust. Optical telescopes show only dark patches that block the light of background stars. When astronomers turn to other parts of the electromagnetic spectrum, a different picture begins to emerge. In the 1970s, radio observations detect a remarkably compact and bright source of emission near the direction of the constellation Sagittarius. This object receives the name Sagittarius A star. The asterisk does not mark a footnote, but signals that it is a special radio source within the broader Sagittarius A region. The radio emission is steady and concentrated within a very small region of the sky. Early measurements suggest that the object is extremely compact, no larger than the orbit of Earth around the Sun. Yet the amount of energy released points to an extraordinary physical process. At first, scientists are cautious. They know that pulsars and other energetic stars can also emit strongly at radio wavelengths. Still, the center of the galaxy appears unique. This compact source does not pulse like a neutron star, and its spectrum extends from radio into infrared and even into the X-ray domain. Such behavior indicates an environment with intense gravitational and magnetic energy. As technology advances, astronomers return to this region again and again. In the 1980s and 1990s, new radio interferometers allow them to improve the sharpness of their images. The Very Large Array in New Mexico and later the Very Long Baseline Array provide a way to measure structure on millisecond scales. The position of Sagittarius A star is confirmed as stable at the exact dynamical center of the Milky Way. This stability is important. Ordinary stars wander across the sky, but Sagittarius A star remains fixed, suggesting it is anchored by enormous gravity. Meanwhile, near-infrared telescopes open a fresh window. On Earth, infrared light is blocked by water vapor in the atmosphere, but observatories placed on high mountain sites like Mauna Kea and the Atacama Desert can peer through. Detectors track the positions of individual stars close to the galactic center. For the first time, astronomers can watch stars complete partial arcs of their orbits around an unseen central object. The possibility of a massive black hole comes into sharper focus. The center of the Milky Way is about 26,000 light-years away from Earth. From this distance, the scale of motion is tiny on the sky. A star must be tracked over many years to reveal even a small change in its path. Teams led by researchers using the Keck Observatory in Hawaii and the Very Large Telescope in Chile dedicate decades to this effort. They develop techniques like speckle imaging and adaptive optics which correct for the blurring caused by Earth's atmosphere. The result is a series of maps showing stars moving in tight ellipses around the exact position of Sagittarius A star. One of the most important stars is called S2. This star completes an orbit roughly every 16 years. As it approaches closest to the center, it moves at several thousand kilometers per second faster than almost any other known star. The orbit is closed and consistent with the gravitational pull of a single compact mass. By applying the laws of orbital mechanics, astronomers determine that about 4 million times the mass of the Sun is concentrated within a volume smaller than our solar system. No cluster of faint stars, no group of neutron stars, and no cloud of dark matter can explain this level of compactness. Only a supermassive black hole fits the evidence. The discovery is not a single sudden announcement, but the gradual accumulation of many lines of data. Each observation narrows the possibilities. The stability of Sagittarius A star as a radio source indicates an object of extreme density. The orbits of stars show the invisible mass that must lie at the center. The comparison with other galaxies also adds weight. Many bright galaxies exhibit active nuclei powered by matter, falling into supermassive black holes. Although the Milky Way is quiet today, its central object matches the expected pattern. Even the size of the source, as measured with very long baseline radio interferometry, supports this interpretation. Radio waves from Sagittarius A star pass through turbulent plasma in the inner galaxy, which blurs the image. Yet when corrections are applied, the intrinsic source size is found to be on the scale of a few times the Schwarzschild radius of a 4 million solar mass black hole. The Schwarzschild radius is the mathematical boundary inside which escape becomes impossible, sometimes called the event horizon. The fact that Sagittarius A star is smaller than any cluster of objects of comparable mass rules out alternative explanations. By the early 2000s, consensus is strong across the astronomical community. Sagittarius A star is recognized as the supermassive black hole at the center of the Milky Way. Nobel Prizes in physics are later awarded to researchers who pioneered the observations of stellar motions confirming the reality of this hidden object. What began as a faint radio point in the 1970s becomes a central anchor of modern astrophysics. At the same time, Sagittarius A star remains faint compared with black holes in active galaxies. It does not blaze with brilliant jets or devour large amounts of matter. Its quiet nature makes its discovery even more subtle. Instead of overwhelming radiation, astronomers must rely on precise measurements of motion and gravity. The compact radio source is a steady beacon, but it is the behavior of the surrounding stars that confirms the black hole beyond reasonable doubt. Once Sagittarius A star is identified as the compact source at the heart of the galaxy, the next task is to measure its influence with as much precision as possible. The stars that orbit close to the center provide the clearest evidence. They act as traces of the hidden mass, their paths revealing the invisible pull that guides them. Each star is followed carefully year after year by observatories equipped with infrared detectors and adaptive optics. Their positions shift slightly from one observing season to the next, and when the data are combined across decades, the orbits emerge with striking clarity. These orbits are not random but organized into ellipses, each centered on the same invisible point. The star called S2 is the most famous. It completes its journey around the center in about 16 years, and at its closest approach it comes within about 17 light hours of the central object. To picture that distance, it's about 3 times the diameter of the orbit of Pluto. At such proximity, S2 rushes through space at over 7,000 kilometers per second, more than 2% of the speed of light. No other object could hold a star in such a tight, fast orbit, unless it were enormously massive and compact. From S2 alone, astronomers infer that about 4 million solar masses lie within a region no larger than our solar system. S2 is not the only messenger. Other stars, sometimes called the S-stars, as a group follow different orbits, some with shorter periods and some more elongated. Together they create a 3-dimensional map of the gravitational potential. By fitting the paths with models, astronomers refine the mass estimate and confirm that the central mass does not wander. The black hole itself remains invisible, but its gravity is imprinted on every star nearby. These measurements are made possible by advances in adaptive optics which use deformable mirrors to correct for atmospheric distortion in real time. Without such corrections, the stars near the galactic center would blur into a haze of light. With them, each star is resolved sharply enough to track its motion from year to year. The precision reaches the level where relativistic effects can be seen. As S2 swings close to Sagittarius, a star its light is stretched by the intense gravity, producing a gravitational redshift. This shift is measured in the infrared spectrum and matches the prediction of general relativity. The orbit of S2 also shows a slight precession, meaning that the ellipse slowly rotates over time. This effect is similar to the well-known precession of Mercury around the Sun, but much stronger due to the greater mass and compactness of the black hole. These observations make the galactic center one of the best laboratories for testing gravity in the strong field regime. To reach these results requires extraordinary patience. The teams at Keck and the Very Large Telescope devote decades to continuous monitoring. Each night of observation yields a few positions, and only after years can the full arc of an orbit be traced. The long time span is a challenge, but it also brings confidence. With each completed orbit, the mass estimate becomes more secure. The consistency across different stars rules out the possibility of a cluster of smaller objects. Such a cluster would scatter the stars through gravitational encounters, but instead the orbits remain smooth and Keplerian, dominated by a single central mass. The density implied is beyond comparison. If the 4 million solar masses were distributed as normal stars, the cluster would shine brightly and be easily visible. If the mass were composed of neutron stars or stellar black holes, they would collide and merge within a short cosmic time, leaving behind a single larger black hole. If it were a concentration of dark matter, it would need to be confined in an impossibly small region. The only plausible conclusion is a supermassive black hole. Even as the orbits confirm the mass, they also raise new questions. The S-stars are young, with ages of only a few million years. Their presence so close to the black hole is surprising, since the tidal forces should inhibit star formation. One possibility is that they formed farther out and migrated inward through dynamical interactions. Another is that they were born in a disk of gas that once circled the black hole and later dispersed. Either way, their youth challenges models of how stars can survive and evolve in such an extreme environment. Astronomers also note the distribution of eccentricities and inclinations among the S-stars. Some orbits are nearly circular, while others are elongated and tilted at various angles. This variety suggests a complex history of dynamical processes, perhaps involving resonant relaxation or encounters with passing clusters. The orbits are not simply the product of isolated two-body interactions, but the outcome of many gravitational influences in a crowded environment. The monitoring of these stars is now carried out with exquisite accuracy. Positions are measured to within milliseconds, and radial velocities to within a few tens of kilometers per second. These measurements allow scientists not only to weigh the black hole, but also to look for deviations that could signal additional physics. For example, any deviation from the predictions of general relativity would be immediately apparent in the precession of the orbits or in the timing of the closest approaches. So far, the data remain consistent with Einstein's theory. This study of stellar orbits at the galactic center has transformed our understanding of Sagittarius A star. It has turned a once uncertain radio source into a well-measured supermassive black hole, weighed by the motion of stars that circle it under the pull of its immense gravity. Each orbit is a precise clock, each pericenter passage a test of the laws of physics. The quiet black hole itself does not announce its presence loudly, but the stars around it act as markers that trace its gravity in the most direct way possible. The galactic center is now the only place in the universe where the mass of a supermassive black hole is determined by watching individual stars complete their paths. This achievement stands as one of the most remarkable successes of observational astronomy in the modern era. Around Sagittarius A star lies a group of stars that continue to draw attention because of their remarkable orbits and properties. These are called the S stars, and they occupy the innermost region around the black hole. Their paths take them through extreme gravitational fields, allowing astronomers to test physical laws at scales that cannot be reached anywhere else in the Milky Way. The cluster is dense, the stars move rapidly, and their arrangement provides crucial information about the central mass and the conditions near it. Unlike typical stars in the galactic disk, these stars do not follow the rotation of the galaxy at large. Instead, they are caught in the gravitational dominance of the central object. The most studied of these stars is S2, but it is only one member of a larger group that numbers in the dozens. Some of these stars have orbital periods shorter than 20 years, while others take longer paths of hundreds of years. Each orbit is mapped by careful observations with large telescopes. Adaptive optics technology has been essential because it sharpens the blurred images caused by Earth's atmosphere and allows astronomers to track the positions of individual stars in the crowded central field. The Keck Observatory and the Very Large Telescope have accumulated long-time series of data that show these stars tracing elliptical orbits around the black hole. The center of all these ellipses coincides with the radio source of Sagittarius A star, confirming again that this is the site of the hidden mass. The properties of the S stars are unusual. Many of them are bright blue stars of relatively young age, only a few million years old. This is surprising because the environment so close to the black hole should be hostile to star formation. The tidal forces of a 4 million solar mass object would be expected to tear apart a gas cloud before it could condense into new stars. Yet the evidence shows that stars do exist and even thrive in this region. The origin of these stars remains an open problem. They may have formed farther from the center and migrated inward through dynamical processes. Another possibility is that they were born within a dense accretion disk that once circled the black hole, providing a shielded environment where gas could collapse. Both ideas are under active study and neither is fully confirmed. The orbital distribution of the S stars is also noteworthy. While some stars follow nearly circular orbits, many others have elongated paths with high eccentricity. The inclinations vary as well, showing that the orbits are not confined to a single plane. This pattern suggests that the stars have been influenced by interactions beyond the simple pull of the black hole. Gravitational encounters among themselves or with other stellar populations may have scrambled their orbits. The concept of resonant relaxation, where torques from the surrounding stars change orbital orientations over time, is often invoked. In such a crowded and energetic environment, orbits are not static but evolve gradually under many influences. The dynamical behavior of the S stars also reveals small relativistic corrections. When S2 and other stars reach their closest approach, the curvature of space-time affects their paths. General relativity predicts a precession of the periapsis, meaning the point of closest approach shifts slightly with each orbit. This is measured and compared against theory, giving one of the most precise strong field tests of Einstein's equations. Similarly, the light from these stars experiences gravitational redshift as it climbs out of the deep potential well near the black hole. By splitting the starlight into spectra and analyzing the shifts of absorption lines, astronomers confirm that the effect matches theoretical expectations. Another striking aspect of the S stars is their extreme velocities. Some reach speeds of several thousand kilometers per second among the fastest stars known in the galaxy. Such velocities make them valuable probes of gravitational physics, because even a small deviation from prediction can accumulate into measurable changes over the years. The careful tracking of their positions and velocities requires consistency across instruments, calibration against background sources, and the use of long baseline interferometry for added accuracy. The result is an unprecedented laboratory for studying gravity in action. Beyond the immediate cluster of S stars lies the nuclear star cluster, a dense concentration of stars that extends over several light-years around Sagittarius A star. This cluster contains both old and young populations, as well as compact remnants, such as white dwarfs, neutron stars, and stellar black holes. The coexistence of such varied objects adds complexity to the gravitational environment. Encounters among stars in this cluster can scatter them onto new trajectories, some leading them inward toward the black hole, and others flinging them outward at high speeds. Indeed, some of the hypervelocity stars discovered in the galactic halo are thought to have originated from such interactions near Sagittarius, a star gaining their enormous speed from gravitational slingshots around the central mass. The nuclear star cluster is extraordinary in its density. Within just a cubic parsec, the number of stars reaches values far beyond what is seen in the galactic disk. This density enhances dynamical processes and shortens timescales for relaxation and scattering. The high density also makes it a prime site for studying stellar evolution under unusual conditions. Stars evolve not in isolation but in constant interaction with neighbours, and under the overarching influence of the supermassive black hole. Collisions, binary interactions, and tidal effects shape their histories in ways not typical for stars farther out in the galaxy. The presence of both the S stars and the larger nuclear cluster illustrates the complexity of the galactic centre. It is not simply a black hole in empty space, but a crowded environment where gravity, radiation, and dynamics intertwine. The black hole dominates the potential well, but the stars supply traces that allow astronomers to measure and test. Each observation contributes not only to understanding Sagittarius A star itself, but also to broader questions of how stars form and survive near black holes across the universe. The evidence gathered from the orbits, the spectral signatures, and the dynamical distribution of the stars has solidified the case that the Milky Way hosts a supermassive black hole, while also opening questions that remain unanswered. The measurements of stellar orbits around Sagittarius A star establish the mass, but the nature of the central object also requires an understanding of how compact it must be. Compactness refers to the degree to which mass is squeezed into a small volume. If 4 million times the mass of the Sun is contained within the orbit of Neptune, that mass density far exceeds what can be supported by any collection of ordinary stars. To explore this, astronomers examine alternative possibilities and compare them against observation. Could the central object be a cluster of neutron stars or stellar mass black holes? Could it be an exotic form of matter unknown in laboratories? The evidence consistently rules out these scenarios. A cluster of ordinary stars of such mass would shine with enormous luminosity, yet no such emission is seen. Neutron stars are far dimmer, but a cluster of millions of them packed so closely would be unstable. Gravitational encounters would cause the cluster to collapse into a single larger black hole within a fraction of the age of the galaxy. Similarly, a cluster of stellar mass black holes would merge quickly, producing gravitational waves and leaving behind one dominant black hole. In all these cases, the timescales for stability are far shorter than the billions of years over which the Milky Way has existed. The very fact that the central mass remains compact and stable today indicates that it must already be a single object. The alternative idea of a concentration of dark matter also fails. Dark matter is thought to be made of weakly interacting particles that do not clump on such small scales. Models of dark matter halos predict smooth distributions extending over many thousands of light-years, not sharp peaks within light hours. If dark matter did accumulate in such a dense ball, It would not remain static but would dissipate or annihilate depending on its particle properties. No current theory allows a dark matter configuration as dense as what is inferred from the orbits of the S stars. Exotic compact objects have also been proposed, such as boson stars or gravitar stars. A boson star is a hypothetical object made of particles that obey Bose-Einstein statistics, allowing them to occupy the same quantum state. In principle, such objects could be massive and compact without forming an event horizon. Gravitar stars are another speculative alternative with an interior of exotic energy surrounded by a thin shell. Yet these models remain theoretical, and none can reproduce the full range of observations. The size of the radio source, the stability of the emission, and the gravitational redshifts measured in nearby stars all fit the black hole interpretation more directly than any exotic alternative. Very long baseline interferometry provides some of the most direct evidence for compactness. By linking radio telescopes across continents, astronomers create an Earth-sized virtual dish with resolution sharp enough to probe scales of tens of microarc seconds. Sagittarius A star is observed to be smaller than expected if it were any kind of star cluster. After correcting for the blurring effect of interstellar scattering, the intrinsic size is consistent with just a few times the Schwarzschild radius. The Schwarzschild radius for 4 million solar masses is about 12 million kilometers, only a fraction of the orbit of Mercury. That the observed source is not much larger than this strongly supports the presence of an event horizon. Accretion physics also reveals compactness. Gas that falls inward heats as it approaches the central object. If there were a surface, the gas would eventually strike it and radiate its energy. This would create a steady and bright signal. Instead, Sagittarius A star is dimmer than expected, consistent with gas, disappearing past an event horizon, rather than piling up on a hard surface. The dimness is explained naturally by a black hole that swallows most of the infalling matter without releasing much radiation. This lack of a surface glow is itself strong evidence that the central object is not an exotic star but a true black hole. The gravitational potential inferred from stellar orbits implies that the density of the central mass exceeds 10 to the 17th solar masses per cubic parsec. This number is so extreme that it dwarfs any known astrophysical system. Star clusters, even the densest globular clusters, reach only a few thousand solar masses per cubic parsec. Neutron stars are dense individually, but cannot exist in stable clusters of millions. The contrast between what is seen at the galactic center and what is possible in ordinary matter leaves no doubt that a qualitatively different object is present. This conclusion is reinforced by comparisons with other galaxies. Observations with the Hubble Space Telescope and ground-based observatories reveal that many galaxies host supermassive black holes at their centers. The masses correlate with the velocity dispersion of stars in the surrounding bulge, a relation known as the M-sigma relation. The Milky Way falls neatly on this relation if Sagittarius A star is taken to be a 4 million solar mass black hole. If instead the center contained some exotic object, it would be an outlier without explanation. The consistency with the behavior of other galaxies suggests that our galaxy is not unusual, but part of a broader pattern, where central black holes are a common feature. The compactness of Sagittarius A star also allows it to serve as a test of general relativity in the strong field regime. Light passing close to the event horizon is bent sharply, producing lensing effects. The orbits of stars precess under the curvature of spacetime. The time dilation near pericenter causes clocks to run slower relative to those farther away. Each of these effects has been measured or is within reach of current technology. The match to predictions is a confirmation not only of the black hole nature of the central object, but also of the accuracy of Einstein's theory under extreme conditions. The designation of Sagittarius A star as a black hole is therefore not based on one line of evidence, but on the convergence of many. Radio imaging shows it is small. Stellar orbits show it is massive. Accretion flow models show it is dim and lacks a surface. Stability arguments show that alternative clusters cannot survive. Comparative studies show that the Milky Way fits into the broader category of galaxies with central black holes. Each line of evidence alone is compelling, but together they form a consistent and nearly unassailable case. The galactic centre is the home of a supermassive black hole as real and as measurable as the stars that orbit it, surrounding Sagittarius. A star is a crowded assembly of stars that together form what astronomers call the nuclear star cluster. This cluster is distinct from the wider bulge of the Milky Way because of its extraordinary density. Within just a few light years of the central black hole, the number of stars exceeds that of almost any other known stellar system. The cluster contains both young and old stars, massive short-lived blue stars, as well as long-lived red giants, and even compact remnants such as white dwarfs, neutron stars, and smaller black holes. The mixture of ages and types reflects a long history of star formation and dynamical evolution in the immediate neighbourhood of the supermassive black hole. The nuclear star cluster is studied mainly through infrared observations, since visible light is blocked by interstellar dust along the line of sight. Adaptive optic systems mounted on large ground-based telescopes provide the necessary resolution to separate individual stars despite the crowded field. Surveys reveal that the stellar population within a few parsecs of Sagittarius A star numbers in the millions. The surface density rises sharply toward the centre, although at the innermost arcsecond the profile flattens into what is called a core rather than a cusp. This core structure is the subject of debate since theoretical models often predict a steeper cusp of stars around a black hole. The difference may be due to dynamical interactions that scatter stars outward, or due to repeated episodes of star formation that alter the distribution. The presence of young stars so close to the black hole is one of the most puzzling features. Star formation requires cold, dense gas that can collapse under its own gravity. Yet the tidal forces of Sagittarius A star should disrupt gas clouds before they can condense. Observations nonetheless reveal populations of young, massive stars in orbits within just a few tenths of a parsec. Some of these stars are arranged in disks, suggesting that they formed from gaseous disks that circled the black hole in the past. Others appear more randomly distributed, perhaps captured or scattered from farther out. The ages of these stars, often only a few million years, point to recent star-forming episodes, meaning that the galactic centre has remained a site of ongoing stellar birth even in the shadow of the supermassive black hole. Old stars are also abundant in the nuclear cluster. Red giants populate the field, but interestingly their numbers seem to decline in the very central region. This depletion of bright red giants near Sagittarius A star is sometimes referred to as a missing cusp. Possible explanations include collisions between giants and other stars that strip away their envelopes, tidal interactions with the black hole that disrupt them, or past episodes of energetic outbursts that altered the stellar distribution. Whatever the cause, the absence of a sharp peak in red giant density remains a clue to the complex dynamics of the centre. Compact objects must also be present in large numbers. Stellar evolution naturally produces neutron stars and stellar mass black holes over billions of years. The gravitational pull of Sagittarius A star should cause these heavy remnants to sink toward the centre, a process known as mass segregation. Although they cannot be seen directly, their presence is inferred from models and from occasional detections of X-ray binaries and pulsars near the galactic center. These remnants interact with the stars around them, exchanging energy and scattering lighter stars outward. The invisible population of compact objects may number in the hundreds of thousands within a few parsecs. The dynamical environment of the nuclear star cluster is extreme. Stellar encounters are frequent compared to the galactic disk. Binary systems are disrupted, and some stars are flung outward as hypervelocity stars escaping the galaxy entirely. Others are perturbed inward and may be tidally disrupted if they pass too close to the black hole. This constant gravitational stirring contributes to the complex distribution of orbits seen in the S-star cluster. The nuclear star cluster is not a static system, but a churning sea of stars influenced by the dominant gravity of Sagittarius A star. Kinematics provide additional insight. Measurements of radial velocities and proper motions of thousands of stars reveal velocity dispersions of over 100 kilometers per second. The motions are not purely random, but show signs of rotation, aligned roughly with the plane of the Milky Way disk. This rotation suggests that at least part of the nuclear star cluster formed from material that settled into the central region from the galactic disk. The mix of random and ordered motion, however, indicates that mergers and accretions have also played a role. The nuclear star cluster is likely the product of both in situ star formation and the infall of clusters from larger distances. Star formation history in the galactic center is reconstructed through spectroscopy, which reveals stellar ages and metallicities. Studies show multiple episodes of star formation over the last 100 million years, with some bursts producing the massive stars seen today. The gas required for such bursts must have been funneled inward through dynamical processes in the galaxy, perhaps driven by the bar structure of the Milky Way or by interactions with giant molecular clouds. These inflows feed not only the black hole but also the central reservoir of gas from which stars can form. The nuclear star cluster also affects observations of the black hole itself. The dense stellar background produces light that can interfere with measurements of faint accretion emission. The gravitational potential of the cluster adds a small but non-negligible contribution to the motions of stars which must be accounted for in models. Understanding the distribution and composition of the nuclear star cluster is therefore essential for isolating the influence of Sagittarius A star alone. The study of the nuclear star cluster is not limited to the Milky Way. Similar clusters are observed in other galaxies, especially those with lower mass black holes. Comparing them provides a broader context. The Milky Way cluster is among the most massive known, consistent with the presence of a moderately massive central black hole. Its mixture of stellar populations, its density profile, and its star-forming history offer a template for understanding galactic nuclei in general. The interplay between black holes and nuclear star clusters appears to be a common feature across galaxies. In this way, the nuclear star cluster is both a laboratory and a companion to Sagittarius A star. It reveals how stars can exist in the most intense gravitational environment available, how star formation can continue in defiance of strong tidal forces, and how dynamical processes shape the heart of a galaxy. Every orbit, every stellar collision, and every burst of star formation adds a layer of complexity to the central region. The stars do not merely surround the black hole, they participate in a continuous dialogue with it, their motions and their lives intertwined with the gravity that anchors the Milky Way. Sagittarius. A star does not exist in isolation. Around it lies a reservoir of gas and dust that spirals inward under the pull of gravity. This flow of material is called accretion, and in most galaxies it powers the brilliant activity of quasars, an active galactic nuclei. In the Milky Way, however, the accretion rate is unusually low. The black hole at our centre consumes matter only sparsely, and as a result it shines with a faint glow compared to its cousins in more active galaxies. Still, the process of accretion is the key to understanding the emission we do detect from Sagittarius A star and the physical conditions near its event horizon. The gas that approaches the black hole originates from the central molecular zone and from stellar winds of the many massive stars in the nuclear cluster. These winds collide heat and form a hot plasma that drifts toward the centre. Unlike the thin accretion disks of bright quasars, the flow here is radiatively inefficient. This means that most of the energy released by falling matter is not radiated away as light, but is carried inward by the gas itself or blown outward in weak outflows. Models of such flows are called radiatively inefficient accretion flows. They explain why a 4 million solar mass black hole that should be extremely bright is in fact dimmer than many individual stars. Radio observations show that Sagittarius A star emits steadily at centimetre and millimetre wavelengths. The spectrum indicates synchrotron radiation, produced by electrons spiralling in magnetic fields at relativistic speeds. This emission comes from the inner accretion flow, where magnetic turbulence accelerates particles. Infrared observations detect variability with flares that rise and fall on timescales of tens of minutes. These flares likely originate from magnetic reconnection events close to the event horizon, where tangled fields suddenly release energy. X-ray observatories such as Chandra and XMM Newton have recorded occasional flares that brighten the source by factors of hundreds for short intervals. The quiescent state is faint, but the flare activity shows that the black hole is not entirely silent. The low efficiency of accretion at Sagittarius A star is partly due to the geometry of the flow. Gas approaches from many directions carrying different amounts of angular momentum. Instead of settling into a thin disk, the material forms a thick, hot structure more like a torus. In this state, much of the matter does not reach the event horizon at all. Simulations suggest that more than 90% of the inflowing gas may be blown away by winds before crossing the horizon. This explains why the black hole accretes at only a tiny fraction of the Eddington rate, the theoretical maximum at which radiation pressure balances gravity. Magnetic fields play an essential role in shaping the accretion flow. Observations with the Atacama Large Millimeter Array reveal polarized emission from Sagittarius A star evidence that magnetic fields are ordered on small scales. These fields thread the plasma and transport angular momentum, allowing gas to spiral inward. They also power the flares when reconnection occurs. The polarization changes during flares suggest that structures close to the event horizon rearrange themselves dynamically. Magnetic turbulence is therefore central to both the steady, faint glow and the brief bursts of brightness. Accretion at Sagittarius. A star also has consequences for the surrounding environment. Even though the energy output is low by quasar standards, it is still significant compared to the local stellar population. The radiation heats nearby gas influences the chemistry of molecular clouds and adds to the pressure that shapes star formation. The outflows from the accretion flow may also carry material outward into the central molecular zone, contributing to turbulence. This feedback is modest compared to active galaxies, but it is a reminder that even a quiet black hole participates in the ecosystem of its galaxy. The timescales involved are short in astronomical terms. Material orbiting near the innermost stable circular orbit completes a revolution in tens of minutes. Flares observed in infrared and X-ray light often follow these timescales, rising and decaying within about an hour. These times match the orbital periods near the event horizon, reinforcing the idea that the emission originates from the very edge of the black hole. The variability provides astronomers with a unique opportunity to study strong gravity, not just through static pictures, but through changes that unfold in real time. The accretion flow has been studied across the spectrum. At radio wavelengths, long-term monitoring reveals both steady emission and occasional variations. At sub-millimeter wavelengths, the spectrum turns over, consistent with emission from the innermost regions. In the infrared, adaptive optics observations catch flares and track polarization changes. In X-rays, satellites provide time-resolved light curves of sudden brightenings. Even at gamma-ray energies, telescopes such as Fermi detect emission from the galactic center, though it is not yet certain how much is directly linked to Sagittarius A star. The multi-wavelength approach is essential because each band reveals a different layer of the physics. The faintness of Sagittarius A star compared with its mass remains one of its most striking features. If the black hole accreted matter at just 1% of the Eddington rate, it would outshine every star in the galaxy. Instead, it accretes at less than 1/1,000,000th of that rate. The explanation lies in the inefficiency of the flow and the loss of material to winds. This makes our galactic center an invaluable laboratory for understanding the low luminosity state of black holes, which is thought to be common in the universe, but is usually too faint to study in detail. Sagittarius. A star is close enough that even its weak glow can be examined with high resolution, offering insights into the physics of accretion at the lowest levels of activity. As technology advances, astronomers continue to refine their view of the accretion flow. The Event Horizon Telescope, a global network of radio dishes, has begun to resolve the horizon-scale structure of Sagittarius A star. The first images released in 2022 show a ring-like feature consistent with light bending around a compact mass. This provides direct evidence that the faint emission comes from gas orbiting near the event horizon. Future campaigns aim to track changes in the image on short timescales, perhaps even watching bright regions orbit as hotspots in the flow. The study of accretion at Sagittarius A star therefore bridges theory, simulation, and observation. It shows how gas from the larger galaxy finds its way to the center, how it interacts with magnetic fields and turbulence, how it radiates as it spirals inward, and how most of it escapes again in winds. The black hole is not an isolated sink, but a dynamic participant in its environment. Even in a state of low activity, it provides a detailed portrait of accretion physics that applies to black holes of all sizes. Every flare, every variation in polarization, and every spectral measurement adds to the understanding of how matter behaves under the most extreme gravitational influence known. Although Sagittarius A star is faint most of the time, it occasionally produces sudden increases in brightness that provide valuable information about its inner regions. These events are called flares, and they are observed in infrared and X-ray wavelengths. The flares occur a few times per day in the infrared and less frequently in the X-ray band, but when they happen, they can brighten the source by factors of tens to hundreds. They typically last from about half an hour to a few hours, rising rapidly and then decaying just as quickly. The timescales involved are comparable to orbital periods near the innermost stable circular orbit of the black hole, suggesting that the flares are generated within a few event horizon radii of the center. Infrared observations with adaptive optics on large telescopes such as the Very Large Telescope and Keck have captured detailed light curves of these flares. They reveal substructure with rapid variations occurring on timescales of only a few minutes. This fine structure points to localized regions of emission, perhaps hotspots of gas that temporarily radiate more intensely as they orbit close to the black hole. Polarization measurements show changes in the orientation of the electric field vector, during flares consistent with the twisting and reconnection of magnetic fields. These signatures support the idea that flares are powered by magnetic processes similar to solar flares, but on a far more extreme scale. X-ray observatories such as Chandra and XMM Newton have provided complementary data. Most of the time, Sagittarius A star emits X-rays at a very low level, but once or twice a day it flares to brightnesses 100 times higher. The X-ray flares coincide with some of the infrared flares, though not always. This suggests that multiple mechanisms may be involved or that the same underlying process produces emission at different energies depending on conditions. The X-ray flares are generally shorter and more energetic, pointing to synchrotron or inverse Compton scattering by highly accelerated electrons near the event horizon. The rarity and unpredictability of the flares make them challenging to study. Coordinated multi-wavelength campaigns are often organized with telescopes across the world and in space observing simultaneously. When a flare occurs, data from radio-infrared X-ray and sometimes gamma-ray bands can be combined to form a more complete picture. These campaigns have shown that the flares are not accompanied by large changes in the radio emission, which remains relatively steady. This indicates that the flares are confined to the innermost regions, rather than propagating outward through the larger scale accretion flow. The physics of flares is closely tied to the properties of the accretion flow. Magnetic turbulence is expected in the hot plasma surrounding the black hole. When magnetic field lines are twisted and compressed, they can reconnect, suddenly releasing stored energy into the surrounding particles. These particles are accelerated to relativistic speeds and emit synchrotron radiation in the infrared. Some of the photons can be boosted to X-ray energies through inverse Compton scattering. The rapid rise and fall of the flares reflect the sudden release of magnetic energy and the quick cooling of the energized electrons. Another possible contributor to flare variability is orbiting hotspots of plasma. Numerical simulations show that turbulence in the accretion flow can create localized regions of enhanced density and temperature. As these hotspots orbit near the innermost stable orbit, relativistic effects such as Doppler boosting and gravitational lensing can cause the observed flux to vary rapidly. Polarization swings during flares are consistent with this picture, as the orientation of emission changes with orbital motion. If this interpretation is correct, then tracking the periodicity in flare substructure could provide direct information about the spin of the black hole, since the innermost stable orbit depends on spin. The observed timescales also constrain the size of the emitting region. A flare that rises and decays within 30 minutes must originate from a region no larger than the distance light can travel in that time, which is only a few times the Schwarzschild radius of the black hole. This places the source of flares firmly within the strong gravity regime. The ability to watch events unfolding so close to the event horizon makes Sagittarius A star one of the few places where dynamic processes at the brink of a black hole can be studied directly. Flares have implications beyond the immediate vicinity of the black hole. They inject energy into the surrounding plasma, which can alter the state of the accretion flow for hours afterward. The infrared and X-ray radiation from flares can also affect the ionization and chemistry of nearby molecular clouds. On longer timescales, repeated flares may contribute to heating the gas in the central parsec, influencing star formation. Although each flare is brief and modest, compared to the power of active galaxies, their cumulative effect may help maintain the energetic balance of the galactic center. Astronomers continue to refine their methods for observing flares. Infrared instruments with higher sensitivity capture weaker flares that were previously undetectable, revealing that variability is even more common than once thought. X-ray observatories maintain long-term monitoring programs to catch the brighter flares. Future missions with higher time resolution and sensitivity will allow detailed spectroscopy of individual events, offering clues about the particle distributions and magnetic field strengths involved. The Event Horizon Telescope may eventually image structural changes associated with flares, providing a direct view of matter in motion near the horizon. The study of flares at Sagittarius A star highlights the contrast between the black hole's general quietness and its moments of activity. Most of the time it emits steadily at a low level, but the sudden bursts show that energy can be released dramatically when magnetic fields and plasma conditions align. These bursts are not just curiosities, they are laboratories where the behavior of matter under extreme gravity, magnetic fields, and relativistic speeds can be tested. Each flare is a window into a regime of physics that cannot be recreated on Earth. To understand the full nature of Sagittarius, us star astronomers strive to resolve the region around the event horizon directly. The technique that makes this possible is very long baseline interferometry, which links radio telescopes across the globe to create a virtual dish the size of Earth. By combining signals recorded simultaneously at sites separated by thousands of kilometers, the angular resolution can reach tens of microarcseconds sharp enough to see structure at the scale of the event horizon 26,000 light-years away. The Event Horizon Telescope collaboration was formed for this purpose, uniting facilities in North America, South America, Europe, Hawaii, and the South Pole. At millimeter wavelengths, the scattering caused by interstellar electrons is reduced compared with longer wavelengths, allowing a clearer view of the galactic center. The Event Horizon Telescope first demonstrated its power by imaging the black hole in the galaxy M87, revealing a ring of emission with a dark central shadow consistent with light bending around an event horizon. Attention then turned to Sagittarius A star. Observations were carried out during multiple campaigns, and in 2022 the first image was released. It showed a bright ring-like structure with a diameter of about 50 microarcseconds surrounding a darker region at the center. This size matches precisely the predictions for a 4 million solar mass black hole at the distance of the Milky Way. The image of Sagittarius A star is blurrier than that of M87 despite being closer and thus larger on the sky. The difference arises because Sagittarius A star is far less massive, so gas orbits around it in minutes instead of days. During the hours required to gather data across the globe, the source changes, creating a blurred average of multiple structures. To address this, the Event Horizon Telescope developed imaging methods that account for time variability, reconstructing the most likely ring structure consistent with the changing emission. Even with this complexity, the result is a clear confirmation of the black hole interpretation, showing that the compact radio source coincides with the expected shadow of an event horizon. The appearance of the ring is shaped by the bending of light in strong gravity. Photons emitted by hot gas near the black hole can orbit multiple times before escaping, producing a bright photon ring. The dark central region, called the shadow, is not the black hole itself, but the projection of the event horizon against the background emission. The size of the shadow depends mainly on the mass of the black hole and only weakly on spin. The agreement of the observed diameter with predictions provides one of the most direct measurements of mass for Sagittarius A star, consistent with values obtained from stellar orbits. Polarization observations add another dimension. The light from Sagittarius A star is partially polarized, indicating the presence of magnetic fields near the event horizon. Maps of polarization from the Event Horizon Telescope reveal swirling patterns consistent with strong organized fields. These fields are responsible for shaping the flow of gas and for producing the flares seen at higher energies. The polarization structure also helps distinguish between different theoretical models of accretion. A magnetically arrested disk, for example, predicts more ordered fields than a turbulent flow, and the data provide constraints on which scenario is closer to reality. The imaging of Sagittarius A star also allows astronomers to test general relativity at the event horizon scale. Alternative theories of gravity can predict different shadow sizes or shapes. Within the current uncertainties, the observed ring is circular and matches general relativity. Future observations with more telescopes and higher frequency coverage aim to sharpen the image further, perhaps detecting asymmetries caused by black hole spin. Detecting spin is challenging because its signature is subtle, but if achieved, it would provide vital information about the history of the black hole, including how it grew over cosmic time. The Event Horizon Telescope operates at a wavelength of 1.3 millimeters, chosen as a compromise between resolution and atmospheric transmission. Observations require exceptionally dry sites such as the Atacama Desert and the South Pole, where water vapor does not absorb the radiation. Coordinating telescopes across continents is a formidable logistical task involving precise atomic clocks to synchronize recordings. The data collected are so large that they cannot be transmitted electronically and must be physically shipped on hard drives to central processing facilities. There, the signals are correlated and combined to reconstruct the final image. The successful imaging of Sagittarius A star is thus not only a scientific achievement, but also a triumph of global collaboration and technical ingenuity. Continued imaging campaigns are planned aiming to watch Sagittarius A star change in time. Because matter orbits the black hole on minute timescales, future movies may reveal hotspots circling the shadow, providing direct visual evidence of relativistic motion. Such time-resolved imaging would open a new era in black hole astrophysics, turning static pictures into dynamic observations. These efforts will be complemented by next-generation instruments that expand the network to include more telescopes, extend baselines, and cover shorter wavelengths for higher resolution. The ability to image the horizon scale of Sagittarius A star is profound. For decades, the existence of a black hole at the galactic center was inferred indirectly from stellar orbits and from the compactness of the radio source. Now the direct observation of a shadow ring provides visual confirmation. It shows that light behaves exactly as predicted in curved space-time, bending into a circle around the invisible mass. This is not an artist's impression or a theoretical diagram, but a measurement derived from photons collected across the Earth. It anchors our understanding of the Milky Way's heart in a way that is both precise and tangible. The close monitoring of stars and gas around Sagittarius A star provides an opportunity to test the predictions of general relativity in a regime of strong gravity. While Einstein's theory has been confirmed in many settings, from the precession of Mercury to the detection of gravitational waves, the galactic center offers a unique laboratory where the curvature of spacetime is extreme and measurable with precision. The orbits of the S-stars are central to these tests. When the star S2 approaches its closest distance to the black hole, the intense gravitational field alters both its trajectory and the light it emits. These changes can be compared directly with theoretical predictions. One of the clearest effects is gravitational redshift. As light leaves the strong gravitational field near the black hole, its wavelength is stretched. During the pericenter passage of S2 in the year 2018, astronomers measured the spectrum of the star with high-resolution instruments on the Very Large Telescope. They observed that the absorption lines of hydrogen and helium were shifted to longer wavelengths beyond what would be expected from the star's motion alone. The size of the shift matched the prediction of general relativity almost exactly, providing a strong confirmation that gravity behaves as Einstein described in the strong field regime. Another relativistic effect is the precession of the orbit itself. In Newtonian gravity, the orbit of a star around a point mass is a closed ellipse. In general relativity, the ellipse rotates slowly with each orbit, causing the point of closest approach to advance. This phenomenon, known as Schwarzschild precession, was first detected in Mercury's orbit around the Sun, but is far stronger near Sagittarius A star. For S2, the predicted precession is about 12 arc-minutes per orbit. Observations before and after the 2018 pericenter confirmed that the orbit had shifted by this amount in agreement with relativity. This measurement is one of the most direct demonstrations of space-time curvature around a supermassive black hole. In addition to these classical tests, astronomers search for more subtle deviations. General relativity predicts that light should bend around massive objects, an effect known as gravitational lensing. Stars passing behind Sagittarius. A star from our perspective should appear slightly displaced, and in some cases their light may be magnified. Detecting these tiny shifts is challenging, but improvements in astrometric accuracy are bringing them within reach. Instruments such as gravity on the Very Large Telescope Interferometer combine light from multiple telescopes to achieve microarc-second precision enough to measure the deflections caused by the black hole's gravity. Time dilation is another consequence of relativity observable at the galactic center. As S2 swings around its orbit, clocks on the star effectively tick slower than clocks far from the black hole. This is not directly measurable with a wristwatch, but is inferred from the combination of gravitational redshift and orbital motion. The consistency of these effects with general relativity provides further confirmation that the theory holds even under the influence of millions of solar masses compressed into a tiny region. Relativity also predicts the existence of frame dragging if the black hole is spinning. This effect, known as the lens-Thirring precession, would cause the orbital plane of stars to shift over time. Detecting this requires extremely precise long-term monitoring of many orbits, since the effect is smaller than the Schwarzschild precession. Astronomers are actively searching for evidence of frame dragging in the galactic center, and future instruments may provide the sensitivity needed to detect it. If found, it would not only confirm another aspect of relativity, but also reveal the spin of Sagittarius A star, a property that remains uncertain. The tests of relativity near the galactic center are important not only for confirming Einstein's theory, but also for probing possible deviations that could signal new physics. Alternative theories of gravity often predict differences in orbital precession, redshift, or lensing. So far, all measurements are consistent with general relativity within observational uncertainties. The agreement strengthens confidence in the theory, but the search continues for any hint of discrepancy. The galactic center offers a regime where such deviations, if they exist, would be most likely to appear. The precision of these measurements depends on technology developed over decades. Adaptive optics corrects atmospheric distortion to resolve individual stars in the crowded field. Interferometry combines light from multiple telescopes to increase resolution further. Spectrographs dissect starlight into its component wavelengths to measure Doppler shift with high accuracy. Each instrument contributes to the chain of evidence that connects the motions of stars to the fabric of space-time itself. The effort involves international teams, years of observations and meticulous calibration to ensure that systematic errors are minimized. While S2 has provided the most detailed tests to date, other stars are now being tracked with similar precision. Some have shorter orbital periods, which will allow relativistic effects to accumulate more quickly. As these orbits are mapped, the dataset will grow richer, enabling tests of gravity with greater accuracy. The hope is that within a few decades, the combined evidence from many stars will allow astronomers not only to measure spin, but also to rule out or support subtle alternatives to general relativity. The galactic center thus stands as a natural laboratory of gravity. Nowhere else are the scales so well matched to observation. Stellar motions can be tracked over human lifetimes, yet the gravitational field is strong enough to reveal relativistic corrections clearly. This combination of accessibility and extremity is unique. The ongoing monitoring of stars around Sagittarius A star ensures that every new pericenter passage adds another piece of data to the test. With each orbit, our understanding of gravity deepens and the predictions of Einstein continue to hold true under the most demanding conditions nature provides. Outside the immediate orbits of the S stars lies a larger structure of gas and dust known as the circumnuclear disk. This feature is a ring-shaped collection of molecular material that extends from about 1.5 to 5 parsecs from Sagittarius A star. It is composed mainly of molecular hydrogen, along with traces of carbon monoxide, ammonia, and other molecules that can be detected in radio and submillimeter wavelengths. The circumnuclear disk is dense, clumpy, and tilted relative to the galactic plane. Its presence shows that even in the harsh gravitational and radiative environment of the galactic center, molecular material can persist and organize itself into a coherent structure. The circumnuclear disk is mapped using instruments such as the Atacama Large Millimeter Array and the Very Large Array. These facilities can detect the rotational transitions of molecules and measure their velocities through Doppler shifts. Observations reveal that the gas in the disk rotates around the central black hole with velocities of over 100 kilometers per second. The disk is not smooth, but broken into dense clumps and filaments, each tens of thousands of solar masses. Some regions are compressed enough to show evidence of recent or ongoing star formation, despite the tidal stresses that act to disrupt them. This raises important questions about how stars can form in such an environment, and how gas is funneled inward to feed the black hole. The disk is not uniform in orientation. Parts of it are warped, suggesting that it has been disturbed by interactions with infalling clouds or by past episodes of energetic activity from the black hole. Shocks and turbulence within the disk are revealed by broadened spectral lines and by the presence of molecules that form in high-temperature environments. These features indicate that the circumnuclear disk is not a static structure, but a dynamic and evolving one shaped by both internal processes and external influences. Within the inner edge of the circumnuclear disk lies a cavity about 1.5 parsecs across that is relatively devoid of molecular gas. This cavity is thought to be maintained by the strong winds from the many massive stars in the nuclear cluster, and by the influence of the black hole itself. Ionized gas streams through this cavity, forming structures sometimes called the mini-spirals because of their appearance in infrared images. These spirals trace the flow of gas inward towards Sagittarius A star, perhaps providing a channel for accretion. The interaction between the circumnuclear disk, the mini-spirals, and the stellar winds is a complex dance that determines how much material eventually reaches the black hole. The circumnuclear disk is also linked to the larger central molecular zone of the Milky Way, a region tens of parsecs across that contains enormous reservoirs of gas. The disk may act as an interface, capturing material from the zone and directing it inward. In this way, the feeding of the black hole is connected to processes occurring on scales far beyond the event horizon. Star formation in the central molecular zone, supernova explosions, and the dynamics of giant molecular clouds all contribute to the supply of gas that can enter the circumnuclear disk. Magnetic fields are thought to play a crucial role in shaping the disk. Polarized emission measurements show that magnetic field lines thread the gas, influencing how it moves and fragments. Magnetic pressure can counteract gravity, supporting the gas against collapse in some regions, while in others it channels flows along specific directions. The interplay of gravity, turbulence, and magnetic fields determines whether clumps-formed stars disperse or spiral inward. Understanding this balance is a central challenge in galactic center astrophysics. The circumnuclear disk also affects the environment of the nuclear star cluster. Its radiation shocks and winds influence the chemistry and temperature of the gas that permeates the region. Some of the young stars near Sagittarius A star may have originated from dense clumps in the disk that migrated inward and survived tidal disruption. If so, the disk has served not only as a reservoir of fuel for the black hole, but also as a cradle of stars. This dual role illustrates the complexity of the galactic center, where feeding and star formation are intertwined. High-resolution imaging continues to refine our view of the disk. Observations show individual molecular clouds within it, some of which show signatures of infall. These clouds may represent the next parcels of material to be accreted by Sagittarius A star. By tracking their motion over time, astronomers can predict how gas flows evolve, and how accretion events may occur in the future. Occasionally, clouds on eccentric orbits are seen plunging toward the center, stretching into tidal streams as they approach. Such events provide natural experiments in how gas interacts with the black hole's gravity. The circumnuclear disk is also compared with similar structures in other galaxies. Many galactic nuclei show rings or disks of molecular gas surrounding their central black holes. The Milky Way's disk is modest in mass and size compared with some, but it provides the closest example that can be studied in detail. By examining it, astronomers can test theories of gas inflow, star formation, and black hole feeding that apply across the universe. The insights gained from our own galaxy inform models of active galaxies and quasars, where the same processes occur on larger and more luminous scales. The presence of the circumnuclear disk demonstrates that even in the most extreme gravitational fields, molecular material can persist and organize into structures. It shows that star formation and black hole accretion are not separate processes, but parts of a continuous flow of matter through the galactic center. The disk is a link in the chain that connects the large-scale structure of the Milky Way to the tiny scale of the event horizon. Its study reveals how galaxies channel gas to their centers, and how central black holes and their environments evolve together. Beyond the circumnuclear disk lies a wider zone of gas and dust that defines the broader environment of the galactic center. This is called the central molecular zone, and it extends for several hundred parsecs along the galactic plane. It is a massive reservoir of dense molecular material containing tens of millions of solar masses in the form of giant molecular clouds, filaments, and turbulent flows. The central molecular zone is the most active star-forming region in the Milky Way, producing clusters of young massive stars as well as fueling the processes that eventually deliver gas towards Sagittarius A star. Its scale and complexity make it both a laboratory for astrophysics and a vital piece of the ecosystem that surrounds the black hole. The gas in the central molecular zone is much denser and warmer than typical clouds in the galactic disk. Observations in carbon monoxide and ammonia lines reveal temperatures of 50 to 100 Kelvin compared to 10 Kelvin in more quiescent regions. The turbulence is also greater, with velocity dispersions of tens of kilometers per second. These conditions result from the gravitational potential of the galactic center, frequent cloud collisions, and the influence of magnetic fields. As a result, the central molecular zone is a site of unusual chemistry, where molecules such as formaldehyde, methanol, and complex organics are detected in abundance. These molecules form in dense environments where shocks and radiation alter their chemical pathways. Star formation in the central molecular zone proceeds in bursts. Clusters such as the arches and the quintuplet, each containing thousands of massive stars, are products of these episodes. The massive stars in turn produce strong winds and supernova explosions, injecting energy back into the gas and stirring the turbulence further. This feedback loop shapes the evolution of the central molecular zone, regulating how much gas remains available to drift inward toward the circumnuclear disk and Sagittarius A star. The balance between inflow star formation and feedback is delicate and changes over millions of years. Magnetic fields are particularly strong in the galactic center. Non-thermal radiofilaments some tens of parsecs long thread the central molecular zone. These filaments are aligned with magnetic field lines and emit synchrotron radiation from relativistic electrons spiraling along them. The existence of such organized structures suggests that magnetic fields are coherent over large distances and play a major role in shaping gas dynamics. They confine plasma-guide cosmic rays and may help channel gas toward the black hole. The interplay of turbulence and magnetic order is one of the defining features of this region. The central molecular zone also contains shells and bubbles of hot gas produced by past supernovae and stellar winds. These structures are visible in X-ray and radio images, testifying to the violent processes that occur in the heart of the galaxy. Some shells are hundreds of parsecs across, showing that feedback from stars can influence the environment on scales much larger than individual clusters. The presence of hot plasma alongside cold molecular clouds creates a multi-phase medium where interactions between components shape the flow of matter toward the center. Infrared and submillimeter observatories have mapped the central molecular zone in great detail. Instruments such as the Herschel Space Observatory and ALMA reveal a twisted ring-like structure of dense gas known as the 100-parsec ring. This ring orbits the galactic center and may act as a staging ground for gas that eventually spirals inward. The ring is clumpy with regions of active star formation interspersed with quiescent clouds. The dynamics of the ring are influenced by the galactic bar, which drives gas inward from larger radii and feeds the central molecular zone. In this way, the structure of the galaxy on kiloparsec scales connects directly to the processes that supply material to Sagittarius A star. The central molecular zone is not only a reservoir of gas, but also a region of intense radiation. Ultraviolet light from massive stars, X-rays from stellar remnants, and cosmic rays from supernovae permeate the zone. This radiation ionizes gas, heats dust, and alters chemical reactions. Observations of ionized lines and recombination spectra reveal regions where radiation dominates, creating extended ionized layers around molecular clouds. These layers are visible in radio continuum maps as thermal emission. The coexistence of ionized neutral and molecular gas in close proximity makes the galactic center a complex and dynamic environment. The conditions in the central molecular zone provide context for the faint activity of Sagittarius A star today. The black hole sits within reach of enormous amounts of gas, yet only a small fraction currently makes its way inward. The reasons for this inefficiency are not fully understood. Turbulence, magnetic support, and feedback from star formation may all act to prevent large-scale inflows. Alternatively, the black hole may go through cycles of feeding and quietude, with the present era being unusually calm. Evidence for past episodes of higher activity seen in outflows and bubbles extending above the galactic plane suggests that the balance shifts over time. Comparisons with other galaxies show that the central molecular zone of the Milky Way is both typical and unusual. Many barred spiral galaxies show concentrations of gas and star formation near their centers shaped by inflows along the bar. The Milky Way fits this pattern, but the detailed mapping available in our own galaxy provides insights impossible to gain elsewhere. By studying our central molecular zone, astronomers learn how galaxies move gas inward, how starbursts are triggered, and how central black holes are supplied with fuel. These lessons can then be applied to interpret observations of distant galaxies where only integrated light is visible. The central molecular zone is therefore not just the backdrop of Sagittarius A star, but an active player in its history. It holds the raw material that can either form stars or feed the black hole. Its turbulence, magnetic fields, and feedback determine the rate at which gas reaches the circumnuclear disk. Its structures from the 100-parsec ring to the long radio filaments reveal the forces at work in the heart of the galaxy. In the end, the faint flickering of Sagittarius A and the vibrant activity of the central molecular zone are two sides of the same system connected across scales of light hours to hundreds of parsecs. The evidence of the present quiet state of Sagittarius A contrasts with signs that it has been more active in the past. One of the most striking pieces of evidence is the existence of enormous structures known as the Fermi bubbles. These are two lobes of high-energy emission that extend tens of thousands of light-years above and below the plane of the Milky Way. They were discovered in 2010 using the Fermi Gamma Ray Space Telescope. Each bubble glows in gamma rays and is filled with hot plasma, and together they resemble a pair of balloons attached at the galactic center. Their origin is still debated, but many researchers link them to an episode of outflow from Sagittarius A a few million years ago. Such an outflow would have released energy equivalent to millions of supernova explosions, inflating the bubbles and leaving them glowing today. Closer to the center, X-ray and radio observations reveal smaller bubbles and lobes extending hundreds of parsecs. These structures overlap with the base of the Fermi bubbles and are interpreted as evidence of the same outburst but on smaller scales. They suggest that the black hole was accreting and releasing energy at a much higher rate than it does now. The duration and power of this event are uncertain, but it may have been triggered by a large influx of gas or by the disruption of a massive cloud or star. The remnants of such activity linger as hot plasma and synchrotron, emitting electrons in the central region. Another line of evidence for past activity comes from reflections of X-rays seen in molecular clouds of the central molecular zone. These clouds act like mirrors, scattering and reprocessing X-rays that must have originated from a bright central source centuries ago. Observations show that some clouds brighten and fade over timescales of years, consistent with light echoes from past flares of Sagittarius A. By mapping these echoes, astronomers reconstruct a history of outbursts over the last few hundred years, revealing that the black hole has undergone episodes of much stronger activity even in the recent past. Jets are another possible sign of earlier outflows. In many active galaxies, supermassive black holes produce narrow jets of relativistic particles that extend far into intergalactic space. Sagittarius A does not display prominent jets today, but radio images reveal filamentary structures that may be relics of weak or intermittent jet activity. A linear feature extending several parsecs from the galactic center has been interpreted as a fossil jet, though alternative explanations exist. If confirmed, it would indicate that even a relatively quiet black hole like Sagittarius A is capable of launching collimated outflows under the right conditions. The interplay between outflows and the environment is complex. Energy released by the black hole can heat and compress gas in the central molecular zone, influencing where stars form. Outflows can also clear cavities, reduce accretion by blowing material away, or in some cases trigger further inflows by driving shocks into surrounding clouds. The Fermi bubbles themselves show sharp edges, suggesting that the energy was released in a relatively short burst, rather than gradually. Understanding how such bursts are generated is an active area of research. It may involve feedback cycles in which the black hole alternates between quiet and active states, depending on the supply of gas. The timescales of these events are important. The Fermi bubbles are thought to be a few million years old, while the X-ray echoes trace events within the last several hundred years. This range shows that the activity of Sagittarius A star varies on many timescales. On human timescales, it appears faint and occasionally flaring, but on geological timescales, it has produced massive outbursts. These changes remind us that black holes are not static, but evolve with their environments, responding to the flows of gas and stars that reach their vicinity. The study of past outflows also provides clues about the spin of the black hole. Spin influences how efficiently energy can be extracted from accreting matter and whether jets can be launched. If Sagittarius A star produced large-scale outflows, it may indicate that it has significant spin. However, direct measurements of spin remain elusive. The distribution and energetics of bubbles and jets provide indirect constraints, but they are not yet conclusive. Future observations may help resolve this question, linking the history of activity to the fundamental properties of the black hole. Comparisons with other galaxies show that such episodic activity is common. Many galaxies with relatively quiet nuclei today show evidence of past outbursts from shock-heated gas to radio lobes. The Milky Way fits this pattern, suggesting that central black holes cycle between active and quiescent phases. The energy released in active phases can shape the evolution of the host galaxy by regulating star formation and redistributing gas. In this sense, the Fermi bubbles and related structures are not just curiosities, but important components of galactic evolution. Multi-wavelength observations continue to refine our picture of these outflows. Gamma-ray telescopes map the extent of the Fermi bubbles. X-ray satellites trace the hot plasma inside them. Radio observatories detect synchrotron emission from relativistic particles. Optical surveys search for associated stellar streams or ionized gas. Together, these datasets provide a three-dimensional view of the structures and their impact on the Milky Way. Numerical simulations attempt to reproduce them, testing scenarios of jet-driven or wind-driven outbursts. While uncertainties remain, the consensus is that Sagittarius A star was far more energetic in the past than it is today. The recognition of past activity emphasizes that the current faintness of Sagittarius A star may be temporary. Black holes can shift states depending on the flow of matter around them. If a large molecular cloud were to fall inward in the future, the black hole could flare into activity once more, perhaps launching jets and creating new outflows. The history recorded in the Fermi bubbles and X-ray echoes shows that our galactic center has experienced such transitions before. It is a reminder that even the quietest supermassive black holes have the potential for dramatic change over cosmic timescales. The environment of Sagittarius A star is not only shaped by gas and stars, but also by radiation fields and magnetic structures that pervade the galactic center. These elements are invisible to the eye, yet they exert profound influence on how matter moves, how energy is transported, and how processes close to the black hole unfold. The radiation field in the inner parsecs is intense, produced by the combined light of millions of stars by hot plasma, heated through stellar winds and by the faint but persistent glow of the accretion flow. This radiation bathes molecular clouds, strips electrons from atoms, and sets the conditions under which chemistry and star formation proceed. Ultraviolet light from massive stars creates extended regions of ionized hydrogen, while X-rays from both Sagittarius A star and stellar remnants penetrate deeper into clouds, driving complex reactions. Magnetic fields add another layer of structure. They are traced by polarized emission in the radio and submillimeter bands, as well as by the remarkable non-thermal filaments seen near the galactic center. These filaments are narrow linear structures that extend for tens of parsecs, shining in synchrotron radiation from electrons spiraling along ordered magnetic field lines. Their orientation and persistence suggest that magnetic fields are coherent and strong in this region, reaching strengths of milligauss compared with microgauss in the galactic disk. Such fields can guide cosmic rays, confine hot plasma, and influence how gas flows toward the black hole. The combination of radiation and magnetic fields shapes the central molecular zone. Clouds exposed to ultraviolet light develop photodissociation regions where molecules are broken apart and ions are produced. These regions emit characteristic infrared lines that allow astronomers to measure conditions such as density and temperature. Magnetic pressure can support clouds against gravitational collapse, delaying or preventing star formation. At the same time, shocks driven by stellar winds or past outbursts from Sagittarius A star can compress magnetized gas, triggering star formation in localized spots. The balance between support and compression determines how the environment evolves. Closer to the black hole, magnetic fields thread the accretion flow itself. Simulations show that turbulence in the plasma amplifies fields through dynamo action, creating loops and tangles. These fields transport angular momentum outward, allowing gas to spiral inward. When field lines reconnect, energy is released suddenly, producing the flares observed in infrared and X-rays. Polarization measurements during flares reveal rapid swings in orientation, direct evidence that magnetic structures are reconfiguring near the event horizon. The dynamics of fields at these scales are crucial for understanding both the steady emission and the variability of Sagittarius A star. The radiation environment also has consequences for time dilation and relativistic effects near the horizon. Photons emitted close to the black hole are stretched by gravity and delayed by curved spacetime. To distant observers, processes appear slowed, an effect that becomes more dramatic the nearer one approaches the horizon. Although this is not directly experienced by matter falling in, it shapes how we observe events. For example, hotspots orbiting near the innermost stable circular orbit may appear to linger or smear due to relativistic lensing and time dilation. These observational signatures are consistent with predictions of general relativity and are now being probed by instruments such as the gravity interferometer. Radiation pressure is weaker in Sagittarius A star than in active galactic nuclei because the luminosity is low. However, on larger scales, the combined output of the nuclear star cluster contributes significantly. The ultraviolet and infrared radiation fields are among the strongest in the galaxy, altering dust grains, heating gas, and driving infrared emission that dominates the central region. Dust absorbs ultraviolet and re-emits in the infrared, creating a background glow that permeates the galactic center. This glow complicates observations, but also provides valuable information about the energy budget of the region. Cosmic rays' high-energy particles accelerated by supernovae and shocks are another component of the environment. The density of cosmic rays in the galactic center is higher than in the disk, inferred from gamma-ray emission produced when cosmic rays collide with gas. These particles ionize molecular clouds, and influence their chemistry, producing molecules such as H3+ that can be detected in infrared absorption. The high ionization rate maintains a level of coupling between gas and magnetic fields, ensuring that magnetohydrodynamic effects remain important throughout the central molecular zone. Magnetic structures also extend vertically out of the plane. Observations reveal large-scale arcs of radio emission that rise perpendicular to the disk, suggesting connections between the central region and the halo of the galaxy. These vertical fields may channel outflows and link to the origins of the Fermi bubbles. If so, they represent the scaffolding through which energy from the black hole and the nuclear star cluster is transmitted to scales thousands of times larger. The coherence of these fields across tens to hundreds of parsecs demonstrates that the galactic center is not a chaotic tangle, but an organized magnetized environment. Understanding these invisible components requires multi-wavelength observations and careful modeling. Polarimetry at millimeter wavelengths traces fields in the innermost accretion flow. Infrared spectroscopy reveals the effects of radiation on molecules. Gamma-ray observations map cosmic ray interactions. Together, these approaches build a picture in which Sagittarius A star sits at the nexus of magnetic and radiative forces that extend across the heart of the galaxy. The black hole is not only a sink of matter but also a source of energy that, together with stars and remnants, establishes the conditions of its environment. The galactic center therefore presents a tapestry where gravity, radiation, and magnetism intertwine. The immense pull of the black hole anchors the stars and gas, while radiation fields and magnetic structures shape how that material behaves. The balance of these forces determines whether gas forms new stars, flows inward, or is blown outward. It is a balance that has persisted for billions of years, producing the complex and dynamic region we observe today. Studying it provides not only insight into our own galaxy, but also a template for understanding the centers of galaxies throughout the universe. Even after decades of careful study, Sagittarius A remains partly hidden in uncertainty. The basic facts are secure. It is a supermassive black hole of about 4 million solar masses. It lies 26,000 light-years away at the center of the Milky Way, and it governs the orbits of nearby stars and gas. Yet many details about its properties and history are not yet resolved. One of the greatest unknowns is the spin of the black hole. Spin describes how rapidly a black hole rotates around its axis, and it influences many aspects of accretion and jet formation. A rapidly spinning black hole can release more energy from matter falling in, while a slowly spinning one extracts less. Spin also determines the location of the innermost stable circular orbit, altering the dynamics of gas near the event horizon. Despite its importance, direct measurements of the spin of Sagittarius A have proven elusive. Several methods have been proposed to measure spin. One is to study the shape of the shadow seen by the Event Horizon Telescope. A spinning black hole should produce a slightly asymmetric shadow flattened on one side. However, the variability of Sagittarius A during observations blurs the image, and current data are not yet precise enough to detect such subtle differences. Another approach is to measure the orbits of hotspots or flares near the horizon. The orbital period of material at the innermost stable orbit depends on spin, so observing periodicities in light curves could reveal it. Some infrared flares show quasi-periodic substructures that may be linked to orbital motion, but the evidence is not yet definitive. The orientation of the spin is also uncertain. If the spin axis is tilted relative to the galactic plane, it could affect the direction of any outflows or jets. The alignment or misalignment between spin and surrounding gas may reveal how the black hole grew. A black hole that accreted steadily from a disk aligned with the galaxy's rotation should have its spin axis parallel to the galactic plane, while one that grew through chaotic infall of clouds or through mergers might be misaligned. Without a firm spin measurement, these scenarios cannot yet be distinguished. The feeding history of Sagittarius A star is another open question. Today it accretes only a trickle of gas, but evidence from the Fermi bubbles and X-ray echoes shows that it was far more active in the past. How often has it switched between quiet and active states? Did it once resemble a quasar blazing as bright as entire galaxies, or has it always been modest in comparison? Simulations of galactic evolution suggest that central black holes experience cycles of feeding and dormancy, driven by inflows of gas triggered by mergers bar dynamics or cloud collisions. The Milky Way's history is recorded in the structures around the galactic center, but reconstructing that history requires disentangling overlapping signals of multiple episodes. The mechanisms behind individual flares also remain debated. Magnetic reconnection is the favored explanation, but alternative models include shocks in the accretion flow or sudden injections of particles. The observed polarization changes support magnetic origins, yet the exact process by which fields rearrange and accelerate particles is not fully understood. Understanding flares in detail could illuminate not only Sagittarius A star, but also the physics of plasma in extreme gravity, a problem of interest across astrophysics. Questions also remain about the role of the nuclear star cluster. How did so many young stars form so close to the black hole? Did they form in situ in a dense disk, or did they migrate inward from larger radii? Why are bright red giants depleted in the central arcsecond? Are collisions and tidal stripping responsible, or does the black hole itself disrupt their envelopes? These puzzles are important because they reveal how black holes influence star formation and stellar evolution in their immediate neighborhoods. On larger scales, the interaction between Sagittarius A star and the central molecular zone is still not fully mapped. How does turbulence feedback and magnetic structure regulate the amount of gas that reaches the circumnuclear disk? Why is the accretion rate so low today, despite the enormous reservoir of material nearby? Are we witnessing a lull between more active episodes, or does some barrier consistently prevent large inflows? Observations of molecular clouds in motion toward the center may provide answers in the coming decades. Another unresolved issue is whether Sagittarius A star has ever produced a sustained jet. Some radio features suggest the presence of a weak or fossil jet, but no clear collimated structure like those seen in other galaxies has been confirmed. If Sagittarius A star is capable of launching jets, then under what conditions do they appear, and why are they absent today? If it cannot produce jets, then what sets it apart from other supermassive black holes? These questions tie back to spin accretion state and magnetic field configuration, linking multiple uncertainties together. The distribution of compact remnants in the nuclear star cluster is also largely hidden. Neutron stars and stellar mass black holes should sink toward the center through mass segregation, but only a handful of pulsars have been detected near the galactic center. The scarcity of detections may be due to scattering of radio waves by turbulent plasma, which makes pulsars harder to see. Yet without more detections, it is difficult to confirm whether the predicted population of compact remnants exists. This unknown affects models of gravitational wave sources, since close binaries of stellar remnants near Sagittarius A star could merge and produce detectable signals. Future observations hold the key to resolving many of these uncertainties. The Event Horizon Telescope continues to refine its techniques, aiming for sharper images and possibly even movies of gas orbiting the black hole. Infrared interferometry with instruments like gravity achieves astrometric precision of tens of microarc seconds, allowing tests of relativistic effects with unprecedented accuracy. New X-ray missions with higher sensitivity may capture weaker flares and provide better spectra of brighter ones. Radio surveys with improved resolution may finally uncover the hidden pulsar population. Each technological advance brings the unknowns into clearer focus. Despite these open questions, the consensus that Sagittarius A star is a supermassive black hole remains unchallenged. The uncertainties concern its details, its spin, its feeding cycles, its precise role in shaping the galactic center, rather than its identity. The unknowns are not weaknesses of the case, but opportunities for further discovery. They remind us that even the closest supermassive black hole studied with the most advanced instruments available still holds mysteries. The pursuit of those mysteries drives ongoing research, linking theoretical models, simulations, and observations into a continuous effort to understand the heart of our galaxy. At the core of the Milky Way Sagittarius, a star acts as the gravitational anchor of the entire galaxy. Its influence extends far beyond the immediate orbits of the S-stars, shaping the dynamics of the nuclear star cluster, the circumnuclear disk, and the central molecular zone. Observations across the electromagnetic spectrum have revealed its mass, its compactness, its dim but variable glow, and its connection to past energetic outbursts. These findings create a coherent picture of a supermassive black hole in a state of low activity, surrounded by a complex environment of stars, gas dust, radiation, and magnetic fields. The presence of Sagittarius A star ensures the stability of the Milky Way's nucleus. Without a central mass, the tightly bound orbits of stars and clouds would not be possible. Its 4 million solar masses anchor the motions of millions of stars in the bulge and provide a center of rotation for the galactic disk. Although it is invisible directly, its gravitational signature is written into the dynamics of everything around it. The star cluster is shaped by its pull, the circumnuclear disk rotates around it, and even the larger bar of the galaxy funnels gas toward it. The black hole is thus not only a local phenomenon but also a structural element of the Milky Way. The study of Sagittarius A star represents a convergence of methods and technologies. Radio interferometry maps its compact emission and reveals its shadow. Infrared adaptive optics track the paths of stars that orbit it at thousands of kilometers per second. X-ray and infrared observatories record its sudden flares. Submillimeter arrays measure the polarization of its light-tracing magnetic fields. Gamma-ray satellites detect the vast bubbles that hint at its more active past. Each technique adds a layer to the picture, and together they form one of the most complete portraits of a supermassive black hole available. One of the remarkable aspects of this research is its timescale. The orbital periods of stars near Sagittarius A star range from a few years to centuries, making it possible for human observers to watch real changes unfold. The precession of orbits, the gravitational redshift, and the time dilation predicted by general relativity have been confirmed within the span of a few decades. Unlike distant quasars that change on timescales far longer than a human lifetime, the galactic center provides tests of gravity that can be repeated and refined in the present era. This immediacy makes Sagittarius A star a uniquely valuable natural laboratory. The environment around the black hole is a microcosm of astrophysical processes. Stellar winds collide and produce hot plasma. Molecular clouds orbit in twisted rings and sometimes plunge inward. Flares erupt when magnetic fields reconnect, sending out bursts of infrared and X-ray light. Outflows inflate bubbles that stretch thousands of light years. All of these processes occur under the influence of gravity so strong that light itself is bent into rings. Each observation therefore reveals not just local dynamics, but also the fundamental physics of matter and energy under extreme conditions. Despite its relative quietness today, Sagittarius A star has clearly shaped the history of the Milky Way. The Fermi bubbles show that it was once active enough to release energy on galactic scales. X-ray echoes prove that within the last few centuries it flared much more brightly than it does now. These records of past activity demonstrate that the black hole is capable of transitions between quiescence and power depending on the inflow of gas. The same cycles likely occur in other galaxies, with black holes alternating between feeding and resting states. The Milky Way provides the closest case study of this universal behavior. The unanswered questions remain compelling. The spin of the black hole is still unknown, and its orientation relative to the galaxy is uncertain. The distribution of compact remnants in the nuclear star cluster is poorly constrained. The mechanisms of flare production are not fully resolved. The reasons for the low current accretion rate, despite the presence of abundant gas, are still debated. These gaps in knowledge are not signs of weakness in the black hole paradigm, but markers of where future progress can be made. Each unresolved issue directs attention to the next generation of instruments and observations. New facilities promise to deepen understanding. The Event Horizon Telescope will add more stations and higher frequency coverage, sharpening images of the horizon. The Extremely Large Telescope will track faint stars with even greater precision, revealing relativistic effects on shorter timescales. The Square Kilometre Array will survey pulsars near the galactic center, using them as precise clocks to probe gravity. X-ray and gamma-ray satellites will continue to monitor flares and outflows. Together, these advances will turn the galactic center into the most intensively studied black hole in the universe. Sagittarius A star also serves as a point of comparison for black holes across cosmic history. Quasars seen at high redshift are powered by the same process of accretion but at far greater rates. Active galaxies display jets and luminosities that dwarf anything seen in the Milky Way today. By studying our own black hole in detail, astronomers gain the physical grounding needed to interpret those distant and energetic systems. The lessons from Sagittarius A star thus extend beyond our galaxy, providing a foundation for understanding the role of black holes in the growth and evolution of galaxies throughout the cosmos. In the end, Sagittarius A star is both ordinary and extraordinary. Ordinary because it fits the pattern found in many galaxies where central black holes are common. Extraordinary because it is the closest example, allowing scrutiny at levels impossible elsewhere. It is a silent anchor whose presence can be traced in the orbits of stars, in the glow of faint radio waves, in the flicker of flares, and in the vast bubbles rising above the galaxy. It stands as the central feature of the Milky Way, unseen yet undeniable, a 4 million solar mass concentration of gravity that continues to challenge and expand human understanding of the universe.